All right, this video is for AP Calculus, and we're going to talk about the first video in a series related to limits and continuity of functions. So this first one's going to be about finding limits graphically and numerically. So first we're going to talk about the idea of what a limit is. So a limit exists if, as you get closer to a specific x value, but not quite reaching that value, let's say we have this target x value of 1, and we want to get close to it, either from the left to the right. If the y value of the function also gets close to a value, let's say 2.2 in this case, then we can say the limit, we write that this way, ln, as x approaches a number, in this case 1, is of some function, so we put, in this case this is f of x, that equals the number 2. Okay, so this is the way we write that a limit exists. The limit as x approaches the target value of x, which in this case is 1, some expression for the function f of x, equals the y value that's being approached. Now, the idea of the limit is that it does not matter whether or not you can actually plug the target x value of 1 into the function. You could have a hole in the function here. That'd be fine, because this is just what y value is being approached when you're in the neighborhood or the vicinity of that target x value. Okay, so yeah, that's written this way. Limit as x approaches some number of some function equals a number, and this number is the number that's being approached. So on its way up here, it might be like 2.05, 2.12, 2.19, 2.199, 2.19999. We don't write those numbers. That's not the limit. The limit is the y value that appears to be being approached. All right, so that's the idea of a limit. We're going to talk about different ways to evaluate it and where they exist. First of all, there are three main methods for evaluating a limit. Numerically, which will always work. We're going to learn that method today, although it is easier to do if you have a calculator, which we don't always have a calculator available. And then graphically, which is easiest if a graph is provided in the problem. Then you can just y inspection, like we did on that last screen, see what y seem to be approaching. Right? And then analytically is a faster way to evaluate, and it's the best way if you're not able to use a calculator and you don't have a graph. So today we're going to focus on methods 1 and 2, and in the next lesson we will look at number 3 in more detail. All right, so to evaluate a limit numerically, since we have to approach a target x value, we just literally take some numbers from the left side and approach, and some numbers from the right side and approach. So if we want to approach first from the left, from lower values on the number line, so we've got this x value 4, and we're approaching from the left. The way we write that is we're going to say x approaches 4, but because we're specifically coming from the negative side of the number line, we're going to put a little negative above the 4 like that. And then what we'll do is we'll just plug numbers that are close to 4 but not quite 4. I'm sorry, actually it's 5. Let me change that because this limit says to 5. Let's make it match the writing here. So let's say the target value is 5, and you're saying x is approaching 5. You're approaching 5 from the left. Okay, and that means that you're going to maybe plug in a 4 and a 4.5 and a 4.9, 4.99, 4.999, and then see what numbers come out, right? Now, this is easiest to do if you have a calculator, because if you have a calculator, then you can enter the function as if you're going to graph it. Now, in this case, this function that we're plugging into is x squared minus 25 over x minus 5. So I could enter that into a function as if I was going to graph it. X squared minus 25 divided by x minus 5. Okay, and then I could go ahead now, instead of graphing it, I'm going to use a table, which is second and then this graph button. And by default, a table will start at 0 and go up by 1 for all the x's. You can change that with the table setting here on a TI-84 or TI-83. You can tell it to take the independent variable and set it to ask, which means it won't fill in any values until you plug values in. Then you can do second graph here. And then you can plug in values like 4, 4.5, 4.9, 4.99, and 4.999. So I'm getting closer and closer to 5, although I'm not actually plugging in the 5. Right? If I were to try to plug the 5 in, then the calculator would say error. And that's because if I plug a 5 into this, that would make this denominator 0, and dividing by 0 is undefined. So we can't actually plug the target value in. But as we get closer and closer to 5, the number that we get out of the function seems to be getting closer and closer to 10. Right? So the way we write that is with what we call a one-sided limit. We say the limit as x approaches 5 from the left of this f of x, and we either have to put the expression or like a label for that function. And then I'm going to declare that that's actually equal to 10, not 9.999, but the value that this is approaching, and that is 10. And then you would also need to approach from the other side. So if you're approaching the 5 from this side, we write that this way, that x is approaching 5, but from plus sign here, from the right side of the number line, the positive side. Right? And then when we plug in numbers that start, say, at 6, 5.5, 5.1, 5.01, 5.001 into the function, right? The y value starts at 11, then 10.5, 10.1, 10.01, 10.001. That also seems to be approaching the number 10. The way we would write that is limit as x approaches 5 from the right of x squared minus 25 over x minus 5 is equal to 10. And since we have the same values, essentially as we approached from the left, we ended up getting closer and closer to a 10. And as we came from the right, we also approached the number 10. That means that the number we're approaching seems to be 10 regardless of which direction we're approaching. So now we can say, therefore, these three little dots are shorthand for therefore, the limit as x approaches 5, but we don't specify a direction. This is a two-sided limit or a full limit of x squared minus 25 over x minus 5 equals 10. And that's the conclusion. So this limit is equal to 10. And this is called numerical evaluation because we're simply plugging numbers in closer and closer to the target value from both above and below. All right, so here's another one that you can try. This is the first one in your packet if you have our practice packets. And I would say pause the video, give it a shot, and then see what you get. All right, so I'm going to go ahead and use a table to plug these in really quickly. Let's see, I've got, let's say they're suggesting some numbers, and there's also a different function here. So I'm going to change my function, y equals, to be parentheses x minus 4 divided by parentheses x squared minus 5x plus 4. All right, and then I'm going to go to my table. I'm going to go up here and enter 3.9, 3.99. Oops. Let me go back here again. 3.9. Enter button to be depressed. 3.99. 3.999. I'm just looking at that. That looks to me like that's 3.448, 3.344, 3.333. Let's do another one. 3.99999. 3.3334. That seems to be approaching the number 3.3. I'm saying 3.3, but it's 0.344, 0.334, 0.333, 0.33334. So this value, limit as x approaches 4 from the right, seems to be approaching 0.333, repeating, which would be 1/3. And if I try numbers from the right here, and they have some suggested numbers we can try plugging in here. Let's go back up here. We'll go like 4.1, 4.01, 4.001, 4.0001. Let me just put a couple extra zeros in there. Right, this also seems to be, it's coming up from numbers from the y values that are below 0.333, but it's getting closer to that same 0.333 number, which also would be 1/3. Therefore, I can say the limit as x approaches 4 without specifying the direction of x minus 4 over x squared minus 5x plus 4 equals 1/3. That's the conclusion. All right, so that's how numerical evaluation works. Second way that we can evaluate a limit is graphically, and this is particularly good if we are provided a graph in the problem, although if it's easy to graph the problem by hand, we can do that even if we don't have a calculator. So we're just looking visually to see on the graph what seems to be approached. So back to this limit as x approaches 5, we would split that into two limits, one from the left and one from the right. We would check the limit as x approaches 5 from the left. So as we approach from the left, as we approach 5, this y value gets getting closer and closer to this value, which is a 10. It's kind of hard to see there because this is laying on top of that. And x approaches 5 from the right of that function is also approaching a 10. So we're approaching a 10 on this side, approaching a 10 on this side. We can visually see that it's approaching the number 10. So we can therefore say, therefore, the limit as x approaches 5 of that function is simply equal to 10. So if you have a graph, or if you can easily make a graph, that's the second way that you can evaluate a limit. Okay, so the other thing we need to talk about is that sometimes at different x values, you'll have a function where at some x values the limit exists, but at other x values the limit does not exist. Right, so what could cause a limit not to exist? Well, the main one is if the value that's being approached from either the left or the right side is not a number. So if it's like an infinity, because we're about to approach a vertical asymptote, the limit's supposed to be a number. And there's some kind of wiggle room there when it comes to infinities and one-sided limits, which we'll talk about in a second. But in general, a limit has to be a number. It has to be the same number on the left and the right that the y is approaching. So if that's not true, either the numbers are not numbers, then you can't have a limit. And then the second thing is, if the values being approached from the left and right are both numbers, but they're not the same number. Right? So either of those two things could cause our limit not to exist at that x value. So let's evaluate a number of these things. This is number 2 in that practice packet. The limit as x approaches 2 from the left of f of x, where this graph defines f of x. All right, so if we're approaching positive 2 from the left side, it means we're approaching here, and it looks like we're in this region of the curve, so that means this y value seems to be approaching the number 1. Okay, because that's that. So I'm going to declare this left-sided limit to be a 1. And then it says limit as x approaches 2 from the right. Okay, so if we approach 2 from the right here, that means we're in this part of the curve where we're getting closer and closer to the number 3. Okay, so that limit exists, that one-sided limit. But because the left limit and the right limit are not the same number, we're violating this second condition. That means there's not a single y value that's being approached. So we have to say, therefore, the limit as x approaches 2 of f of x, and typically we don't put an equal sign here, we just write DNE, which stands for does not exist. That limit does not exist. There's no single y value that's being approached, regardless of how we approach. Okay, so remember, limits are about what happens in the vicinity of the function curve, so or of the target x value. Notice I have open circles here, which means that we don't actually, if we were to try to plug 2 in, it would not be this rule. It would not be this rule. It would actually be this filled in dot down here, right? And so when we actually plug 2 in, we get a third different y value, which is y is -1, something like that. Okay, so how do we get to that? Well, if we want to actually plug the target value itself in, then we have to not use limit notation. We just say f of 2, which means you actually plug the 2 into the function, and that's how we would get the number -1 out. All right. All right, let's take a look at another example. So let me change color here. Limit as x approaches -1 from the right. So -1 from the right means we're approaching this way, and this part of this curve is going off to -infinity here. So that's not a number. So this left-handed limit, you could say does not exist because technically it has to be a number. However, we would actually prefer that you either do this, say it's approaching -infinity, or you can even say it's equal to -infinity to ask your teacher what they want to do. On left-handed limits, if they're not a number but they're approaching an infinity, we get a little bit more information if you actually say which infinity it's approaching. Like in this case, it's -infinity specifically. So you can say it's equal to -infinity or approaches -infinity. Although technically you can also say does not exist because limits have to be numbers. In this structure over here, the limit as x approaches -1 from the left, right? So that means we're approaching the target value this way. We're on this part of the curve, so we're going off to positive infinity. You could either write that as just does not exist, approaches positive infinity, or is equal to positive. right? And as soon as you detect that you have a non-number on either side or both sides, you have to declare that the limit without specifying the direction, the two-sided limit as x approaches -1 of f of x, you're required to say that that does not exist. And the reason is, let's say you did have an asymptote like this, and they happen to both be going to positive infinity. Right? You cannot do arithmetic with infinities. You can't set one infinity equal to another infinity because they're not numbers. So there's no possible way to get the same number on the left and the right-hand side if either of them are an infinity. So automatically, when you detect an infinity on either side, the full limit without specifying direction has to be does not exist. All right, so we've just got a few more examples here. Evaluate these limits either numerically or by making a graph. I think we're going to try this numerically. Let's try that. So maybe we could just quickly do, I'll just focus on the notation that you should use to write what you're doing here. Right, so we have to always think about what's happening on the left and the right. So first I'm going to take the limit, the limit as x approaches this target value 3 from the left. We always have to have a function expression in here. So I'm going to copy that. Okay, and I'm going to do this with calculator graphs, or with calculator functions. So let's go back as if we were graphing this function. So this is x squared minus 25. So x squared minus 25. And then divided by x minus 5. Okay, now we're approaching 3 from the left. So on my table, maybe I would put numbers like 2.9, 2.99, 2.999. Can I see what's going on so far? I can already tell that that's approaching the number 8. Okay, so I'm going to declare that that left-handed limit is equal to 8. And then we will go over here, limit as x approaches 3 from the right, x squared minus 25 over x minus 5, and check with numbers above 3. So we're starting above 3, like maybe 3.1, 3.01, 3.0001. And what is happening here? 8.1, 8.01, 8.0001. Okay, that's also getting close to 8. So you have to show the left-hand limit is equal to value, the right-hand limit is equal to value, and because those are both numbers and they're both equal, you can say, therefore, the limit as x approaches 3 without specifying direction of the function x minus 5 is equal to 8. Do you have to write all this? Absolutely. You have to write every bit of that for full credit. And AP, College Board on their exams are extremely picky about formatting, particularly in the limit section. So everything that you see us doing here, that's what you want to do. Okay, same function for number 4 here, except we're approaching 5. So the only thing we're going to change is the target value. Limit as x approaches 5 from the left, x squared minus 25 over x minus 5. I'm going to pick values just to the left of 5. So let me go left to the top here. How about 4.9, 4.99, 4.999? That should be enough to see what's going on. This seems to be closer to 10. Okay. And then limit as x approaches 5 from the right of x squared minus 25 over x minus 5. We will plug in some numbers starting above 5, like 5.1. 5.01, 5.001. And that also seems to be coming down to the number 10. So since those are both approaching the same y value, we can say, therefore, the limit as x approaches 5 of x squared minus 25 over x minus 5 is, in fact, equal to 10. All right. Let's try another one. Number 5, limit as x approaches 0 of this structure. Okay, we'll say, let's check from the left. Limit as x approaches 0 from the left of 2x over x squared plus 4x. And so let's see, that is, I got to change the function now. So this is going to be 2x on the top of the fraction divided by parentheses x squared plus 4x. Make sure you have parentheses around the 1 there. And around the numerator if it has a plus or minus. We'll go back to the table and we'll go below 0. So 0.1, well actually we want to go below 0. So negative 0.1, negative 0.01, negative 0.001. And this y seems to be getting closer and closer to 0.5. Okay, so let's check from the other side. X approaches 0 from the right. Okay, it seems kind of like pointless to keep writing the same thing over and over again, but technically this is what we have to do if we want to show very formally that we are checking the limits. So let's try numbers like positive 0.1, 0.01, 0.001. And that also seems to be coming up from below, approaching the number 0.5. So therefore, the limit as x approaches 0 without specifying direction of 2x over x squared plus 4x is equal to 0.5 or 1/2. All right, so that's what it looks like if you have just a single rule. Okay, but a lot of times in limit problems, they will define a function that's defined with a piecewise definition, which means there's one rule that we use for the part of the domain x equals 1. We use a different rule for all the x's to the left of 1, and yet another rule for the x's to the right of 1. And if they're asking me to find the limit as x approaches 1, then that means I'm going to have to check individually, like we always do. Limit as x approaches 1 from the left of f of x. Now I'm going to work vertically here. To work vertically, we're going to use an equal sign here, and then I'm going to write, now I'm going to replace this f of x with one of these rules. Right? Only one of those rules applies just to the left of 1. Just to the left of 1 is x is less than 1, which means the rule has to be 3x minus 1 in the region. So I'm going to copy that here, and then I'm going to evaluate that limit. Okay, so if I use a table for that, I can plug in the rule 3x minus 1, and then use a table to come up to 1 from the left. So that would be like 0.9, 0.99, 0.999. And that seems to be getting closer and closer to a 2. So we're going to declare that this limit is equal to a 2. All right, now let's go ahead and do this. Limit as x approaches 1 from the right of f of x. So that is equal to the limit as x approaches 1 from the right of, I have to pick the right rule. So just on this side of f of x, that is this rule, which would be 3x. And so if I plug in numbers above 1, but into this function, which is 3x, not 3x minus 1, we'll delete that out. Different rule on the other side here. I'm going to go to the table here and go to 1.1, 1.01, 1.001, and that appears to be approaching the number 3. Okay, so here's another case where we have a left-handed limit that's approaching a number, a right-handed limit that's approaching a number, but the two numbers are not equal, so we have to say, therefore, the limit as x approaches 1 of, and I'm just going to use the general f of x, does not exist. And this is the right way to show work here. Show the left-handed limit approaching 2, the right-handed limit approaching 3, and then the limit does not exist. You can also write this horizontally if you prefer. Like for this, you would be able to write it like this. Limit as x approaches 1 from the right, from the left of f of x is equal to the limit as x approaches 1 from the left of the rule 3x minus 1, and then assert that that's equal to 2. Okay, so really important, especially with these piecewise defined functions, that you explicitly check the rule on the left and the right, and you make sure you have the right rule. Okay, and then one last one here for this, to wrap up this video. More complicated expression, but it doesn't matter how complicated this is. This table method works all the time. So let's just try that. We're going to plug a function in again to a calculator, as if we are graphing it here. So 1 equals, we will put parentheses on the numerator x minus 1 divided by parentheses x cubed minus 1. And then we'll do a table. We're plugging in numbers below 1, so 0.9, 0.999. Okay, as we get closer to 1, this number gets closer to 0.333. So I would write that this way. Limit as x approaches 1 from the left of x minus 1 over x cubed minus 1 is equal to 0.333, which is 1/3. And then we're going to check from the right. Limit as x approaches 1 from the right, x minus 1, x cubed minus 1. So we have to come down to 1 from higher numbers. So like 1.1, 1.01, 1.001. And those numbers also seem to be approaching 0.333. So 1/3. Therefore, we can say the limit as x approaches 1 of x minus 1 over x cubed minus 1 is equal to 1/3. So the point of this example is no matter how complicated this is, you can always try this numerical method, which is to plug numbers in that are nearby. All right, that'll wrap up this video. We'll talk about a completely different way to evaluate limits in the next video.